Okay, these are the equations about electricity and magnetism and just being able to talk through how you would use them and in what sort of context. This first part is about just finding the force between two charged particles. Sorry about the highlighting there. 1 over 4 pi epsilon naught is a constant, which is on the front side of the sheet. Q1, Q2 are the two charges, and R squared, or R, is the distance between them. That allows you to find the electrical force. The next one is be able to find basically the definition of electric field, which is force per charge. Effectively, it's the force that would be in the spot if there were a charge located there. The next one is finding the electric field for the particular case of a point charge. So it's 1 over 4 pi epsilon naught, Q over R squared. Notice that the only difference between that and the force between two charged particles is just that the top one has Q1, Q2 over R squared, and this just has Q over R squared. Again, because electric field is force per charge, so you lose one of those sort of charges there. The next ones are talking about energy. This is saying the electrical potential energy of something is Q times the voltage, because the definition of voltage is energy per charge. This is for how to find the voltage for a particular point charge thing. That's 1 over 4 pi epsilon naught Q over R. This next equation is what relates the electric field to the voltage. This is the times when you would use this would be in the context of, you remember when we had those contour plots, and we realized that the electric field is where the voltage is changing the fastest. This equation is basically what emphasizes that. It says that it's change in voltage over change in R, so change in distance. So when it's changing fast, you have a big E field. These next 3 equations are about, actually 4 equations, excuse me, are about capacitors. Capacitors I usually think of as 2 parallel plates. This is basically the definition of capacitance right here. It says the change in voltage is the charge per charge divided by the capacitance of that particular setup. Capacitance is measured in farads, remember? This is the formula and how it relates to the geometry of a particular thing. Kappa is the dielectric constant. That's basically how insulating the material is in between the 2 plates. Epsilon naught is a constant, and A is the area, D is like the area of the plates, and D is the distance between them. This next one is how to find the electric field between 2 parallel plates. It's Q over epsilon naught A. And this last one is how to find the potential energy that's stored. Sorry about that highlighting. The potential energy that's stored in a parallel plate capacitor. It's either 1/2 QV, which is the same thing as 1/2 CV squared. You just use those two depending on which things you know. If you know Q and V, use the first part of the formula. If you know C and V, use the second one. That's kind of it. This next little bit is about electric circuits here. So this is basically the definition of current. It's charge per time. This next one is how you find the resistance of a particular object. Rho is the resistivity, L is the length of the wire, and A is the cross-sectional area. This next one is the power that's being dissipated in a particular circuit element. Power, remember, is energy per time. So it's basically how fast something is using energy. You particularly use this when you're talking about resistors. So it's I times V. If you know the current and you know the voltage change across that particular resistor, then you multiply those two and you can tell me the power that's being used by that resistor. The next equation is kind of the classic one. It's I equals V over R, maybe V equals IR. It's called Ohm's law. It's what relates current, voltage, and resistance. These next 2 equations are about resistors in series or resistors in parallel and how they add up. So remember that when resistors are in series, they just add up one after the other. Series is when they're just back to back to back. Parallel is when they're side by side. And then notice this version of the formula is 1 over R equals the sum, that's what this notation says, of 1 over Ri. That means you're summing up all the inverses of all the resistors. What that ends up doing is that the total resistance is always less than each of the individual resistors. That's like, remember how we had, if you have multiple doors that are side by side, it's always easier than if you just had one door. Okay, this next 2 equations are about capacitors in series versus in parallel. Capacitors add exactly the opposite way. This says that capacitors in parallel just add up, just one plus the other, whereas capacitors in series, you have to do 1 over and the 1 over thing. The reason for that is that capacitors in series kind of have to share their charge. so they don't get as much. Whereas capacitors in parallel, they don't share anything. They just each get their own drop, so you have to add them all up. That's the way I kind of think of it. Then we're starting to talk about magnetic fields. This is the magnetic field due to a single long charged wire, or charge carrying wire, so current wire. So it's mu naught I over 2 pi r, mu naught being a constant, I being the current in the wire, and r being the distance you are away from the wire. There's the piece that you need to know about magnetic fields that's not on this formula sheet is you need to remember the right-hand rule. So make sure you have a good, solid understanding of the right-hand rule and how it applies. First rule of the right-hand rule is make sure you use your right hand, please. Okay. Once you know the magnetic field, you could then figure out how you get a magnetic force on an object. These two formulas right here are really the same thing. One of them is the most general version. It's QV cross B, but really that means it's QV sine theta times B, or QVB sine theta. That tells you if you know the charge, the velocity, and the magnetic field strength, you can figure out the force. Most of the time those are 90 degrees, so the sine of theta is 1, so you don't have to worry about the sine of theta. But if it wasn't 1, all it tells you is that you only get to count part of the V and B, and the sine theta tells you how much you get to count. So that's for one particular charge moving through the magnetic field. The next one is if you have a whole current, like a wire, and it tells you that the force on that is ILB sine theta, or just IL cross B. Again, I is the current, L is the length of the wire, B is the magnetic field, and sine theta is the angle between the B field and the current. There you go. These last four are about electromagnetic induction and electromagnetic flux. It's for figuring out how much current you get and how much voltage you get if something about the magnetic field is changing. Again, these first two really tell you the same thing. First one is a dot product. It's B dot A to find the magnetic flux. That's what phi B is. But really, more typically, you would think of that as B times A times the cosine of theta. What that means is that if the two things are, if the B field and the area and the loop are basically perpendicular to each other, then you get to count it all. And if they're parallel to each other, you get nothing. And that's why the cosine theta works on that one. These last two, this is the most general one. It tells you that induced voltage, that's what this little EMF symbol is on the left side. So the induced voltage is equal to the negative change in flux with respect to time. So change in flux over change in time. The minus sign tells you that the voltage opposes that change, and the changing with respect to time means something has to actually be changing there. So the area has to be getting bigger or smaller, or the magnetic field has to be getting bigger or smaller. Something has to do it. The last formula is for the very particular case of a wire moving or a loop moving into a constant magnetic field, and you're trying to figure out the force in the EMF induced, the voltage induced. It tells you that it's the B field times the L times the velocity. That L is the perpendicular length compared to the direction it's moving. That's almost more confusing. I sort of find it easiest to use this first one and just make sense of what I'm doing, but the last one is for that particular case. I think that's it.